We defined weight yesterday as the force of gravity acting on an object, right? It was m times g, as opposed to mass, which is the amount of matter that's possessed by something. One of those two values, either mass or force of gravity, mass or weight, stays the same no matter where you go in the universe. We can be on Earth at sea level, we can be on Earth at the top of Mount Everest, and we can be on Earth, we could be on Jupiter or the moon, and this would stay the same. Which is it? Is it mass or is it weight that stays the same? Mass stays the same. The amount of matter that you possess doesn't change no matter where you go. The weight is dependent upon mass, but it's also dependent upon the acceleration due to gravity. G, sometimes we call it, sometimes we just call it A. Its value would be, on Earth, about 9.81 meters per second squared, depending upon where you are on Earth. The next term we defined yesterday was the normal force. It was related to weight. Does anybody remember how it was related to weight, what the relationship is between normal force and weight? Yep. Yeah, the weight, of course, is how heavy you are, and the normal force is how heavy you feel. You don't perceive your weight. Right now, you think you weigh, I weigh 150 pounds, okay? Let's say you feel like you weigh a certain value, 130 pounds for some of you, 115 pounds for some of you, 150 or 160 pounds for some of you, okay? The weight that you feel isn't actually your weight. The weight that you feel is the normal force. We define the normal force as the force of the floor or whatever it is it's pushing on you. Maybe it's your desk. Maybe it's your car, the seat in your car. Maybe it's the roller coaster track. Okay, maybe it's the airplane, okay, that's pushing up on you. Not quite up, specifically at 90 degrees. So if you're on the ground, the normal force would be pushing directly up on you because that's 90 degrees to the ground. But if you're on an incline like this, the normal force would be pushing at 90 degrees to the ground, which is at whatever height or at whatever angle there. Maybe you're on a roller coaster upside down like this. I'm not sure why you'd be standing upside down in a roller coaster. My suggestion would be to try to avoid this, standing upside down in a roller coaster. Usually you're supposed to sit. But if you were standing there, the normal force would be acting this way, at 90 degrees to the surface. Okay. Now, the force, when we calculate that force, and we're going to learn how to do that soon, when we calculate that value, that's the weight that you feel. In 2 months, when we go to our Physics of Amusement Park ride at West Edmonton Mall, you're going to find yourself upside down in a roller coaster. And at some point, you're going to close your eyes upside down in a roller coaster, and you're not going to know whether you're right side up or upside down. Okay? Your weight is, if you're sitting on the ground, you would think that your weight would tell you whether you're right side up or upside down, but it doesn't. Since your apparent weight is pushing you this way, it feels as if you're being pulled down by gravity this way, right? Normal force is the apparent weight. It's the force of the ground, for lack of a better term, pushing up on something at 90 degrees. The last force that we talked about was the force of friction, and that's the one that we're going to talk about in more detail today. Friction is that resistive force, a force that resists motion. Sometimes it acts on an object that's at rest, resisting motion. Okay, right now Tyler's desk is at rest. No friction acting on it right now. But if I give his desk just a little bit of a push and his desk doesn't move, well then something had to counter that applied force. It was friction. If I push it and it moves, we know that there's still friction between the desk and the ground that resists motion. So it's the force that acts between two surfaces that resists motion. Now, today we're going to distinguish between two types of friction. The first kind of friction is called static friction. It's the force of friction that prevents, or at least tries to prevent, an object from beginning to move. At some level, we know intuitively, Sam, that static friction exists. You push on a big, heavy object, you can't move it, you can't move it, you can't move it. Why not? Because there's friction that's trying to keep it from beginning to move. Now, sometimes you can actually overcome that force of static friction and the object begins to move. Sometimes you can't. Sometimes static friction is so big that you can't overcome that value. Your applied force isn't bigger than static friction. Now, here's what's kind of crazy about static friction. It's not a constant value. It varies. The value of static friction is determined by, well, partly the two materials that are in contact with each other, but it's also partly determined by how hard you push. That's odd. That's really odd, hey? The desk leg and the floor are certain materials. They'll have a certain value of friction acting between the two of them. But what I'm saying, and that's fairly intuitive, I think, but what I'm saying here, right here, that it varies, it's equal to the applied force until a maximum value. What we're saying there is that the harder we push, the harder friction pushes back. It's the stubborn force. I push on something, hey, it pushes back. I push on something harder, it pushes back harder. It can't lose. Static friction doesn't want to lose. I push with a certain force, it pushes as hard as it has to push in order to keep the object from beginning to move until it reaches a maximum value, and then it can't push any harder. So let's say that I push on Tyler's desk with a force of 2 newtons. Doesn't move. Static friction must have been 2 newtons opposing my applied force. Let's say I push on Tyler's desk with a force of 10 newtons. Desk doesn't move. Static friction pushed back this time with 10 newtons. Push back harder. It's the stubborn force, remember. It pushes back as hard as it needs to push. Push on it with 20 newtons. His desk still doesn't move. Static friction is getting even more stubborn. It's pushing back even harder. It wasn't pushing back with 20 in the beginning, only when it needs to push back with 20. Push back with 21. Oops, it moves. The value of static friction was equal to whatever force I pushed with until it reached the maximum value of 20 newtons. And then what happened? Well, then I overcame static friction by 21 newtons, and it moved. Well, then friction isn't static anymore, because you're not trying to keep an object from beginning to move. Now it's kinetic friction, or dynamic friction, sometimes we call it, because the object is moving. Kinetic friction, or sometimes they call it dynamic friction, is that force of friction that acts against something that's already moving. So I pushed with 2 newtons on Tyler's desk, didn't move. Friction was 2 newtons. Static friction was 2 newtons. Pushed with 10 newtons, didn't move. Static friction was 10, opposing the force that I pushed with. Pushed with 20, didn't move. Static friction must have been 22. Pushed with 21, it moved. It's no longer static friction, it's kinetic friction. It's now the force of friction that acts against an already moving object. The nice thing about kinetic friction, though, it doesn't change. Okay, static friction, in the case of Tyler's desk, was 2, it was 10, it was 20, depending upon how hard I pushed. Kinetic friction, let's say it's 17 newtons. 17 newtons, no matter how hard I push, as long as the object is moving. It's a constant value. And it's lower. It's lower in value than the maximum friction force, static friction force. So what was the maximum static friction force in the example of Tyler's desk? 20 newtons. Kinetic friction would be 15, 16, 17 newtons. Kinetic friction is lower, not than the 2 newtons or the 10 newtons that I pushed his desk with, but it's lower than the 20 newtons, the maximum possible static friction. That's why when you push something, you guys have all seen this before, you've all experienced this before. You push something, it's hard to get moving. Okay, you're pushing, you can't get it moving. Finally, it moves. It starts sliding. And then all of a sudden it becomes easier to push, right? You guys ever notice that? It's easier to push once you get it moving because kinetic friction is lower than the maximum static friction. I was pushing with 2, with 10, with 20 newtons on Tyler's desk. Doesn't move. Once I finally get it moving by applying 21 newtons, now I only have to apply 16 newtons, and it's going to keep moving because kinetic friction might be 16. Does that make sense? That's why, by the way, the difference between static friction and kinetic friction, the difference between, or the significance of kinetic friction being less than the maximum force of static friction. That's why when you put on your brakes on ice, you don't want your wheels to lock. Right now, you have what's called anti-lock brakes. What happens is a computer pumps your brakes hundreds of times per second to keep them from locking up. Okay, when I was learning to drive, anti-lock brakes were kind of just starting. Some vehicles had them, some vehicles didn't. Now they all do. I was taught when you start sliding on ice, get your foot on the brake, but pump the brake. Okay, pump that brake with your foot. Now you don't have to do that because the computer does it for you. But I was taught to pump the brake so that the wheels wouldn't lock up. We don't want the wheels to lock up because if we lock the wheels up, then the wheel is sliding on ice. And sliding on ice is kinetic friction. If the wheel is turning, then the same point on the wheel isn't sliding along the ice. It's not moving relative to the ice if the wheel is still turning. That's static friction. Static friction is bigger than kinetic friction. If we're on ice, we want bigger friction, right? So we want static friction. That's why we want the wheels to stay moving. As counterintuitive as it seems, we're trying to stop. We want the wheels to stay moving. Because if they don't, we're dealing with kinetic friction instead of static friction. Let's give you a couple of equations here. There are two, and they look remarkably alike. We're going to say the maximum force of static friction, this is a tongue twister, FSF max. Say that 5 times fast. FSSF. Yes, I know I did. On the first one, too. Can't even say it once, let alone 5 times. The maximum force of static friction. The maximum force of static friction is equal to a Greek letter. It's called mu. It's called mu, and it stands for the coefficient of static friction. The coefficient of static friction is a value that is a constant depending upon the two materials that are in contact with each other. It is a value whose magnitude depends upon how much those two objects or those two materials will stick together. If you've got two materials that like to stick together lots, then you've got a high coefficient of static friction. If you've got two materials that don't like to stick together lots, then you've got a low coefficient. For example, rubber on pavement would be a fairly high coefficient of static friction. Rubber on ice would be a fairly low coefficient of static friction because they don't like to stick together very much. It's equal to the coefficient of static friction. It's equal to mu times the normal force. The normal force is the force of the ground pushing up or pushing at 90 degrees to the surface. When you see this equation, understand that it's not giving you the force of static friction. It's giving you the maximum force of static friction. Let's go back to Tyler's desk example for a second. I pushed with 2 newtons, didn't move. Pushed with 10 newtons, didn't move. 20 newtons, didn't move. 21 newtons, it moved. If I was to calculate the maximum force of static friction there in that problem, don't have enough data, but let's say I did, then the value that I would get would be the 20. That's the maximum force of static friction, not the 2 or the 10 or anything in between. This number is the maximum value. Static friction, it can be lower than the maximum value. The max value here was 20 newtons. I pushed with 2, didn't move. Pushed with 10, didn't move. 7 doesn't move. 8 doesn't move. 3 doesn't move. 19 doesn't move. Static friction is however hard I pushed, not 20. It's however hard I pushed. But the maximum value would be 20 newtons, or mu times the normal force. the force of kinetic friction, what do these vertical lines mean? Yep. The absolute value. So it's a force. There's a direction associated with the force, but this equation won't tell us what direction that is. We have to figure that out some other way. The force of kinetic friction is equal to mu, which is, well, this time it's going to be the coefficient of kinetic friction, which is going to be a different value than the coefficient of static friction. Higher or lower? Remember, it's a measure of how much two things stick together. Do two things stick together more when they're moving, or do two things stick together less when they're moving? Less. The coefficient of kinetic friction would normally be less than the coefficient of static friction. It's equal to the kinetic friction coefficient times the normal force. Looks almost the same as the other equation, except that our coefficient has a subscript k instead of a subscript s. Two different numbers. Also note one more thing. In the static friction force, the value that we solve for is not the value of static friction at any given moment. It's the maximum possible value. It's not the 2 or the 10 in Tyler's desk's example. It's the 20, the maximum possible force. Kinetic friction equation, on the other hand, is the force. When we calculate its value, it's not how hard we're pushing. The force of kinetic friction is mu times the normal force. Does that make sense? So let's go back to Tyler's desk again for a second. I push with 2 newtons, doesn't move. What kind of friction do I have? What kind of friction do I have if his desk doesn't move when I push it? Yep, static, right. Now, what's the value of static friction when I push on it with 2 newtons? And it doesn't move. 2 newtons. Push on it with 10 newtons, doesn't move. What kind of friction do I have? Static. What's the value of static friction? 10 newtons. Push on it with 15 newtons, doesn't move. What kind of friction do I have? Static. What's the value of static friction? 15. Push on it with 20 newtons, doesn't move. Static friction, force of friction is 20 newtons. Push on it with 27 newtons. It moves. What kind of friction do I have? What kind of friction do I have when I push on it with 27 newtons? And it moves. This time it's kinetic friction, right? What's the value of kinetic friction? Maybe 16, maybe 17. We'd have to calculate its value, right? Okay, let's say it's 17. Push on it with, what did I say, 29 newtons? 27 newtons? It moves, kinetic friction kicks in, and now its force of friction is 17 newtons. What if I push on it with 100 newtons? Does it move? Yeah, move to 27 newtons. What kind of friction do I have? Kinetic friction. What's the value of kinetic friction? 17. Kinetic friction increased in value as I was pushing it harder and harder and harder until I exceeded the maximum value. Kinetic friction, once it's there, and it stays the same value no matter how hard I push. So you got to push harder and harder and harder to overcome that stubborn force, static friction. But kinetic friction is kind of the lazy force. Yeah, I'll push back. I'm not going to push any harder though. You push harder on me? Yeah, okay, whatever. You can have it. You can win. Let you win. There's the stubborn force, and then there's the lazy force. They both push back, but one pushes back as I push harder. The other one's just like, here you go. I'll push back with a token force, and that's going to be the force that I always push back with. All right. Oh boy, here's a table. You don't have to copy these down, by the way. They're in your textbook. We'll have a quiz on this tomorrow, by the way. I'm not going to ask you all of these. I'll just ask you 5 of them. Okay? And you just give me the 5 that I ask you. No, I'm not going to give you a quiz on that. If you need these numbers, and you will, for a quiz or a test, I'll give you those numbers. Okay? They might not be in the form of the table, It might just be, here's the value of static friction, here's the value of kinetic friction, and so on. But you'll have the numbers that you need. Take a look at some of these values, though. Notice, first of all, that the value of coefficient of static friction is bigger than the coefficient of kinetic friction in each of them. Notice that some of these have a really big coefficient of friction, say static friction between copper and copper. Some of them have a really low coefficient of friction, like, for instance, synovial fluid on a joint, 0.01. What is that, by the way? What's synovial fluid? It's what keeps your elbow from doing as you move your elbow, right? You need a lubricant in your joints. Otherwise, things are going to rub together, and A, they're going to hurt a lot, and B, they're not going to be nearly as efficient. So you need a really, really low coefficient of friction there, right? Our bodies have been designed to have a really low coefficient of friction in the joints. Skis on snow. Hey, look, you ever try, who's a skier here? Isn't it nice when it's kind of a trade-off, but the skiing itself is nice when it's about -10. You go outside, you go to the hill, you're skiing, it's -10. The snow is dry, okay? As long as you have decent snow, it's really good skiing. Now, it gets a little bit chilly towards the top of the hill sometimes, because if it's -10 at the bottom, it's -20 at the top. Okay, but the snow is good. Okay, you glide along the snow nicely. Do you ever notice, though, in those days when it's maybe +3, +4, +5, it's really nice as far as temperature goes. You could probably even go without gloves because it just seems so warm. You ever notice, though, that skiing isn't very good? Like, your skis don't glide along the snow very well? Look, the coefficient of kinetic friction, and that's usually what we're dealing with skis, right? 0.14 between wet snow and skis. That's more than 3 times the value of kinetic friction between dry snow and skis. So what do you want to ski on? Dry snow, right? Dry snow, -10 snow, not +4 snow. All right, let's take a look at a problem, understanding that we're going to have to refer back to that table as we do this problem and other problems. It says 3.17 on page 185. A sled with waxed hickory runners rests on a horizontal, dry, snowy surface. So we're dealing with waxed hickory runners and dry, snowy surface. Those are my two materials. Now, I can find the coefficient of friction between hickory skis. I'm not sure that anybody actually has hickory skis anymore, but for argument's sake, let's say they do. I guess it's a sledge, right? Still probably don't have hickory skis, but hickory and dry snow. Okay, we know the two materials. We can find the coefficient of friction between the two, but we don't yet know whether we're dealing with static or kinetic friction. Calculate the mass of the sled if the maximum force that can be applied to the sled before it starts moving is 46 newtons. Okay, let's go back to Tyler's example for a second here. When I pushed on his desk, I pushed harder and harder and harder and harder, and it didn't move. The maximum force that I could apply before it began to move was 20 newtons. That was the maximum force of static friction. Not necessarily the force of static friction at any given time, but it was the maximum value. How hard I could push before it moved. And I'm pushing with 8 newtons right now. Okay, doesn't matter. I could push with 20 newtons before it began to move. So we would say the max force of static friction there was 20. Here we're going to say the max force of static friction it's equal to mu times the which is the coefficient of static friction times the normal force. Now, the normal force can be any one of a number of values depending upon a number of factors. But for us right now, it will be the same as gravity. For us right now, it'll always counter gravity. So we're going to say the normal force is m times g. That's not always the case. Okay, but it will be for you guys until further notice. So, Julia is equal to the coefficient of static friction times m times g. We're solving for m. We know the max force of static friction. We don't know necessarily what the force of static friction is at any given time, but the maximum value is 46 newtons. Coefficient, dealing with static friction here, right? So coefficient of static friction between waxed hickory and dry snow. Let's go down here. Waxed hickory, dry snow, 0.06. So let's solve for the coefficient of static friction here now. It's 46 divided by 0.06 times 9.81. And let's do this on our calculator up here just to make sure that you can all do it. Say 46 divided by bracket 0.06 times 9.81 and that bracket 78.15. 78.15, something's wrong with that. No, that's right. We got 78.15 newtons, which technically should be rounded to how many digits? It's kind of odd, but Nathan? No. No. Force is 2 digits. Gravity is 3 digits. The coefficient of friction is 1 digit. So technically, this should be rounded to 1 digit. 8 times 10 to the 1 newtons. That looks really odd, but technically that's correct. Let's take a look at these 2 questions at your desk for the next few minutes, and we'll see what we can do with them. Have a look up here. We're going to do question number 2 as a group here. It says, suppose the sled in example 3.17 is resting on a horizontal wet snowy surface. We need to know something about the sled in example 3.17. Looks like the mass of it was 78.15. That should have been 78.15. Solving for the mass there, right? Should have been 78.15 kilograms, not newtons, right? Okay, so we got the mass of this sled. 78.15 kilograms. We want to know if it moves if I apply a force of 125 newtons on it. Well, we know what the coefficient of friction is because it was waxed hickory and dry snow, I think, wasn't it? Waxed hickory and dry snow. Let's get the maximum possible force of static friction. Let's get, in the example that I keep giving you in class here, let's get that 20 Newton value. How hard you have to push before it begins to move. So let's say FSF max is equal to mu times the normal force. Mu for static friction is 0.06. And we multiply that by the normal force, which is 78.15 times 9.81. At least for now, it's still m times g. Let's get the value for that. You get 45.99 newtons. Anybody else get that? Does it move? Is there a mistake there? Is it on wet snow? I think it was. Oh, yeah. It is, yeah. So it's going to be, yeah, you're right. It's on wet snow, so the coefficient is going to be 0.20. All right, let's try multiplying those those 3 numbers together. 0.2 times 78.15 times 9.81 gives me a force of 153.3. Does it move? No, it doesn't move. Hey, what is the value of friction right now? In this problem right now, what's the value of friction? 150. Who says 153 newtons? The hands go down. A couple hands go up and then look around. Oh, better put the hands down because nobody else is raising their hands up. Nobody says 153? Who says 125? Yeah. The value of friction is not what I calculate there for FSF max. The value of friction is how hard I push if I'm under the maximum value. So it's going to be 125 newtons. The answer is no, it wouldn't move. And the value of static friction, if we were asked that value, is not 153, it's 125. Let's try one more example here. It says a 1640 kilogram lift truck with rubber tires is skidding on wet concrete with all four wheels locked. What's the acceleration of the truck? Well, first of all, clearly a friction problem, right? Are we dealing with static friction or kinetic friction? The rubber tires is skidding on the wet concrete. It's sliding on the wet concrete. Nathan? Kinetic. We're going to say the mass of this object is 1,640 kilograms. We're going to say between wet concrete and rubber, it's going to be 0.5 coefficient of kinetic friction. Notice there are no units with the coefficient, just a number. We want to find the acceleration. Any ideas? Any ideas, sir? Yep. Yeah, we get the mass. We're going to find something here. It's going to be the force, right? Force of friction. It's kinetic friction. The force of kinetic friction is mu times the normal force, which is 0.5 times 1640 times 9.81. Gives me 8044.2 newtons. That's my force of friction. And it's kinetic. It's moving, it's sliding, skidding. Let's find the acceleration by saying A is equal to F over M. It's that Newton's second law equation that I learned the other day, Monday. Force here, 8044.2 newtons, divided by the mass of 1640. I get 4.91. Or technically, should be one digit, right? Technically, it should be 5. Let's try a couple that go with that. Or at least one, I should say, that goes with that. Hey, do you know why I've scratched out question number 2? Read it for a second. Read it and tell me why I've scratched it out, why we don't have to know how to do that yet. We will have to, but not yet. Yeah. Yeah, it's going downhill. And if it's going downhill, the normal force isn't straight up and down, right? So that means it doesn't counter gravity. Not completely, at least. So we don't know what the normal force is yet. We're going to have to learn a little bit more analysis before we figure out what a normal force is on an incline like that. So just question number 1 right now. We'll see how that goes. This one says an applied force of 450 newtons is needed to drag a 1,000 kilogram crate at a constant speed. Hey, good question, because it not only requires us to know this stuff about friction that we're just learning, it also takes us back to the very beginning of this unit, the first day when we talked about Newton's first law, which says, if you remember, an object in motion will continue in motion in a straight line at a constant speed until acted upon by an unbalanced force. It's what we call translational equilibrium. Remember that? Translational equilibrium. This is in translational equilibrium. It's going at a constant speed. What's the net force? What's the unbalanced force if something's going at a constant speed? Maybe you got a force of friction to the right of 100 newtons. Something else must be pushing it to the left at 100 newtons if it's going to keep going at a constant speed. The forces have got to balance. Well, if you need to push it with 450 newtons, and it goes at a constant speed, then friction must be 450 newtons the other way to balance the 450 applied force. If it goes at a constant speed, the forces have got to balance. Friction has to be 450 backwards. So we're going to say force of friction here, kinetic friction because it's sliding, it's moving. We're going to say the force of kinetic friction, 450 newtons, divided by the normal force, which would be 1,000 times 9.81. And when we do that math, we should get 0.0459. No units, just 0.0459 or 4.59 times 10 to the minus 2. What was the problem with that one for those of you who got it wrong? Was it the constant speed thing? Not knowing what force was the friction force? It moves at a constant speed. Forces got to balance. Okay, even if you're not told friction, it's got to be opposite to the applied force. One more example, and then we're done for the day. Well, one more example, then I'm done for the day. You've still got more work to do, but I'm done for the day. Here's the example. As a 10-kilogram object is at rest on a surface that has a coefficient of friction, static friction of 0.95 and dynamic or kinetic friction of 0.65. What's the force of friction? A, if a 50 Newton force is applied to the object, and B, if a 300 Newton force is applied to the object. Here's what I want to do first. Let's get the maximum possible force of static friction. We don't know that that's what friction is, but let's get that value first. FSF max, maximum force of static friction, is equal to mu times the normal force. 0.95 times, assuming it's on a flat horizontal surface, it's m times g, or 10 times 9.81. 93.195 newtons. All right. When I apply a force of 50 newtons on the object, does it move? Boy, Tyler knows the answer to this. No. What do I have to apply in order to get it moving? What do I have to apply to get that object moving? I have to apply, just over 93.195 newtons. Okay. If I push it that hard, it stays at rest. If I push it a tiny little bit more, it moves. That's the maximum possible static friction force. If I don't exceed that, it doesn't move. And if it doesn't move, it's static friction. And static friction is simply the value that I'm pushing with. So it's 50 newtons. What if I added another question there? What if I applied a force of 79 newtons? What would the force of friction be then? 79 newtons. What if I added 92 newtons in there? What would the force of friction be? 92 newtons. But if I'm applying a force of 300 newtons, which is more than the maximum force of static friction, all of a sudden it moves now. Now it's kinetic friction. Let's get the value of kinetic friction. It's equal to 0.65 times 10 times 9.81. For that, I get 63.765 newtons. Notice kinetic friction is bigger than static here. But notice kinetic friction is smaller than the maximum static here. So if I push on it with 50, force of friction is 50. Push on it with 80, friction is 80. Push on it with 92, friction is 92. Push on it with 300, friction's 64. Push on it with 18,112. The force of friction is 64. Once I get it moving, kinetic friction is always the same.